Hey guys, so welcome back to another lecture video. This is a continuation off of the previous lecture video. Um, and so in the last lecture video, last part of that lecture video, I asked you guys to associate or draw the titration curve for each and every single one of these analytes if they were titrated with either a strong acid or a strong base. So let's go ahead and quickly go over the answers. Here, ammonium is a weak acid. And so because it's a weak acid, so we're going to consider all of these substances our analytes, it's going to be titrated with a strong base. And since it's a weak acid, its initial pH is going to be greater than 1 or 0. That's why I'm drawing it higher up. And since it's an acid, the general trend of the curve, of the titration curve, is going to look like an S for this monoprotic acid. And so its equivalence point, it's going to be greater, the pH is going to be greater than 7. Okay. And so if you guys were able to associate those features, these three features, to NH4+, then you guys are on the right track. So let's go ahead and do the next one, Cn negative. This is going to be our weak base. So once again, we're going to consider Cn as our analyte. And since it's a weak base, we know that the curve is going to go from the bottom to the top, from the top to the bottom, I apologize. And since it's a weak base, it's not going to start at 13 or 14. It's going to start at pH that's less than 13. And then we're going to draw a titration curve that's going down. And then once again, it's going to curve off as we get to, when we pass the equivalence point. And so let's go ahead and talk about the equivalence point, which is another feature. Here in this case, the equivalence point is going to be less than 7. Oops, why am I writing K? All right. And so if our hydroiodic acid is our analyte, we know that this hydroiodic acid is a strong acid. So we need to titrate it with a strong base. And since it's a strong acid, the initial pH is going to be close to 1 or 0. That's why I'm putting my initial value all the way at the bottom. And then I'm going to go ahead and curve this titration curve from the bottom to the top. And my equivalence point is going to be at a pH of 7.00. And so if my analyte is a strong base, I know that I'm going to go from basic to acidic, so my curve is going to go down, but my initial pH is going to be very high up. It's going to be either 13 or 14 or around that range because I have a strong base. And so we're going to go ahead and draw the titration curve going down, and the equivalence point is going to be 7. So the pH is going to be at 7 for a strong base, strong acid titration, or strong acid, strong base. All right, so you guys hopefully understand those key features for titration curves. Hopefully you guys, if you guys have any questions, you guys can always email me. But hopefully you guys are able to understand, my train of thought, my logic when approaching these problems. Okay, so make sure you guys are paying attention to the initial pH and the pH at the equivalence point. right, so the last item that we're going to talk about for this chapter is choosing pH indicators. And so pH indicators, they are organic compounds that are weak acids and weak bases. However, these compounds are cool because they're colored. It's a chromatic compound. And so I'm going to go ahead and abbreviate indicator as IN. And so it turns out that when the indicator is in their acidic form, it's going to produce one type of color, or it can be colorless, right? And if we convert the acidic form of this organic compound into its basic form, it's going to turn into another color, or it's going to turn colorless, or it can go from colorless to color. So for example, like phenolphthalein, right? So phenolphthalein went from colorless to pink, and if we went in the reverse, we can go from pink to colorless if our solution in our analyte was basic to begin with. Okay. And so what's really cool is that these pH indicators, they signal the endpoint of our titration. And the endpoint of our titration should represent, equal moles of acid to equal moles of base. And so when you guys are performing titrations, what you guys are used to working with is phenolphthalein. However, phenolphthalein is not the only pH indicator out there. There's a whole bunch of organic dyes. And so depending on the type of titration that you guys want to perform, you guys will choose a specific indicator to signal the endpoint of the titration. And to do that, you guys want to compare a couple of things. You guys want to compare the Ka of the indicator, and you guys are going to express that Ka as a pKa value, just to make it comparable to pH, right? So notice that there's P's on both sides. So we're not going to associate Ka to concentration of hydrogen ion. It's going to be the pKa to the pH. And the pH that you guys want to refer to is the pH at the equivalence point. And so, for example, if your pH, if the equivalence point is at a pH of, for example, 10.00, you want to use an indicator that has a pKa value that's plus or minus 1 pH unit of your equivalence point. So hopefully that made sense. Let's go through an example. So for example, the indicator is going to be bromophenol blue. And so it turns out that the acid ionization constant for bromophenol blue is 1.00 times 10 to the negative 4. Therefore, its pKa is just the negative log of it, which is just 4. And so if the pKa of bromophenol blue is 4.000, its useful range to signal the endpoint of titration is going to be plus and minus 1 pH unit. Okay? And so in this case, the useful range for bromophenol blue is between 3.0 and 4.6. So it's not exactly at 5. It's probably because of the fading in the color or some other reason. But what this is telling you is that if your equivalence point has a pH between 3.0 to 4.6, you guys can use bromophenol blue to signal the endpoint of that titration. Now, another substance is another indicator is methyl red, and so the useful range of methyl red is 4.2 to 6.3. Okay. Now, if you look at both of these ranges, notice that the pH at the equivalence point is less than 7. And so what analyte do you think we will, what analyte do you think our substance will be? What type of analyte will our substance be if the pH at the equivalence point is less than 7? Do you think the analyte is a strong acid, strong base, weak acid, or weak base? Okay. And so if you recall from our titration curve, if you have a pH, an equivalence point pH that's less than 7, then the analyte was a weak base to begin with. Okay. And so that was when you had an initial pH that's less than 13, and its equivalent point, let's just say that 7 is here. Okay, so if we kind of go across, the pH is going to be less than 7. So you guys can probably use bromophenol blue or methyl red to signal the endpoint if your pH, if the equivalence point of your pH is somewhere along this range. Now, what would you choose over another? It really depends on the titration. So for example, if the pH at the equivalence point is like 3.5, then it would probably make sense for me to use bromophenol blue. The range for methyl red is limited between 4.2 to 6.3. And so it turns out that these the useful range of each of these indicators can imply what type of analyte it should be used for. Okay, so we're kind of going backwards in this case. So let's talk about phenolphthalein. Phenolphthalein is that indicator that you guys have used in first semester general chemistry. It goes from colorless to pink. And so it turns out that the pKa of the indicator is 9.3. If you guys want to calculate the Ka of this, just take the 10 to the negative 9.3, and that should give you your Ka value. And so since its pKa value is 9.3, it has a useful range that's plus minus 1 pH unit. And so it turns out that the useful range is between 8.3 and 10. Okay. And so in first semester general chemistry, when you guys were using phenolphthalein, that implied that the pH at the equivalence point should be between 8.3 and 10.0. And so the equivalence point is somewhere along the basic range. And so what does that imply about the analyte? Okay. If the pH at the equivalence point is more basic, what type of analyte do we have? Do we have a strong acid? Do we have a strong base? Do we have a weak acid? Or do we have a weak base? Okay. And so since the equivalence point, since the pH at the equivalence point is greater than 7, it's not at 7, it's greater than 7, then that means that our analyte must be a weak acid. Okay. And so if you guys recall, for weak acids at the equivalence point, I'll just draw it out. When it reacts with that strong base, okay, it's going to produce water and A minus. So HA is just my general weak acid. And so since we're at the equivalence point, that means that all weak acid is reacting with the hydroxide, leaving us with just our conjugate base. And so since this conjugate base is a weak base, some fraction of this weak base is going to go in the reverse direction, producing some hydroxide. And so that's going to make our pH more basic at the equivalence point. Okay. Whereas, so hopefully you guys understand the explanation. So the answer is, the analyte was a weak acid if we're using phenolphthalein as our pH indicator. And so to explain the previous point, if we're using bromophenol blue or methyl red, if you look at their pH range, the pH of the indicator is less than 7. And so we typically use it for analytes that are weak bases. And so why? I'll go ahead and just write down the reaction real quick. So a weak base is, for example, A minus. And when you react it with a strong acid, it's going to produce HA. And so at the equivalence point, we know we have equal amounts of base and acid. So they cancel each other out, and we convert everything into HA. And so we know that since HA is a weak acid, is a conjugate weak acid of A minus, some fraction of it, not a lot, is going to ionize and go back in the reverse direction to reproduce this H plus. And so since some H plus is formed, then that means that the pH at the equivalence point is going to be acidic. Okay. All right. So this is pretty much it for pH indicators. So hopefully you guys can go kind of forwards and backwards with using a specific indicator for a specific analyte. In addition, you guys should, for example, if I give you a list of pH indicators as well as their pKa's and their pH range, you should be able to kind of link which pH indicator to use for a specific titration. All right, guys. So that's pretty much it for this lecture video, and that's pretty much it for this chapter. So the next chapter that we're going to cover is KSP, and I'll make it and post it sometime in the near future. Have a good one.